video is on resonance and formal charge. So if we start out by drawing the Lewis structure for a nitrate ion, we can draw it with a double bond on the left between the nitrogen and oxygen here, and a single bond between the nitrogen and the oxygen on the right, or we can draw it with a single bond between the nitrogen and oxygen on the left and a double bond between the nitrogen and oxygen on the right. Both of which are Lewis structures for nitrate, but they look different based on where the double and single bonds are. So if we were to ask ourselves how many valid Lewis structures are there, we'd say there's two. We can draw this one or this one. However, we know because of research that this is not exactly the case. Because if this drawing were to hold true, then we'd have to have one short bond between the nitrogen and oxygen on the left and one long bond of our single bond on the right, or vice versa, a long bond on the left and a short bond on the right. But we know that that's not true. Because of something called resonance, we can show two equivalent nitrogen-oxygen bonds, each with equal length between a single and a double bond's length. So before we talked about how single bonds were longer than double bonds, but when we go ahead and we draw these, we don't draw them as one being much longer than the other. That's because there's something called resonance occurring. This happens when there is more than one valid Lewis structure for a particular compound. This means that what really is going on is a hybrid, kind of a superimposing of this structure over this structure, where we have 1.5 bonds here and 1.5 bonds here, that we don't necessarily have a perfect double bond on one side or on the other, because remember, our electrons are really swarming all over in their orbitals. We'll notice that this type of resonance occurs a lot with oxygen. Really, electrons are delocalized and can move around in a compound. Furthermore, if we look at our nitrate ion and we attach it to a carbon, we see that this resonance still occurs on the nitrate between the oxygens and the nitrogens. Here I have a double bond and a single bond there. When I am showing that I have resonance, I put an arrow between my two structures to show that this can happen or this can happen, which really means there's a hybrid between the two. Formal charge plays a role into our resonance structure. Polyatomic ions contain atoms that can exceed octet rules, and they have more than one possible Lewis structure. If we were to look at benzene, C6H6, I would draw my 6 carbons, and benzene likes to form a ring, and then there's a hydrogen off of each carbon. Okay. Now, I can't add any more hydrogens. The only thing I can do now is add double bonds. So carbon needs to be bonded to 4 with 4 different bonds. So every other bond is going to be a double bond, and the other ones are going to be single bonds. I can have benzene that looks like this, or because of resonance, my double bonds can happen on the opposite bonds. So my double bonds would be here, here, and here. And because benzene does this, we draw benzene with a symbol to show that this resonance happens. You'll see in textbooks, you'll have a benzene drawn with a circle in the middle. And this is because we know that these are not perfect double bonds and single bonds, but really it's like a bond and a half around because of this delocalization of the electrons. And so we show a benzene like so. So formal charge helps us distinguish which Lewis structure is the most appropriate to have. Formal charge is a numerical difference between the number of valence electrons in the free atom and the number of valence electrons assigned to the atom in our Lewis structure molecule. And we can remind ourselves that these are different than oxidation numbers. So some things to remember with formal charge is the sum of the formal charges must equal the charge on the ion. So if you had nitrate, your total charge between the formal charges of all its components would have to be -1. Atoms are going to try to achieve formal charges as close to 0 as possible. And negative formal charges should always reside on the most electronegative atom. So if I were to look at xenon tetraoxide, I put my xenon in the middle, and I have my 4 oxygens coming around. And if I were to figure out my formal charge of my xenon, well, the normal charge, or my normal number of valence electrons of xenon is 8 because it's a noble gas. The number of valence electrons assigned to the atom in the molecule is 4 because I have 1, 2, 3, 4 that are then getting shared out. So 8 minus 4 gives me an overall charge of positive 4, and so xenon's overall charge is plus 4. And then each of my oxygens that I have, oxygen has 6 valence electrons in its free atom. In my molecule, it has 2, 4, 6, 7. So minus 7 means it overall has a charge of minus 1 for its formal charge, and that's on every one of these because they all look the same. And then overall, the sum of my formal charges must equal the charge of my molecule. So overall, it's 0. So positive 4 minus 4 is 0.